The proton has a mass of 1.67 times 10 to the minus 27 and a charge of 1.6 times 10 to the minus 19. Hence why we say it's roughly got a mass of 1 and a charge of plus 1. The neutron's got a mass of 1.67 times 10 to the minus 27 kilograms. Sorry, I should have said the kilograms. It's got no charge, obviously, because it's a neutron. The electron has got a charge of 9.11 times 10 to the minus 31 kilograms, and it's got a charge of the opposite of the proton, which is minus 1.6 times 10 to the minus 19. Now, the first thing you may be asked to do is use specific charge. Now, specific charge is very easy. It's charge over mass, and the units are coulomb kilograms to the minus 1, so ckg minus 1. Now, it's basically your protons and your electrons over the entire mass of your atom. That's the easiest way of working it out, effectively. But usually, if you want to make life a bit simpler for yourself, work out how many protons there are, work out how many electrons there are, minus 1 from the other, and then put it over that. That's probably the easiest way of doing it, or save you loads of excess calculations. There are 3 types of decay. There is alpha decay, beta decay, and gamma decay. Now, alpha decay is the emission of an alpha particle from a nucleus. It's got to be a big nucleus, so think kind of uranium, plutonium. The particle's made of 2 protons, 2 neutrons, so it's got mass number 4, proton number 2. Then there's beta decay, which gives you beta minus or beta plus, and this involves either an electron or a positron being emitted from the nucleus. And also, if it's a beta minus particle, it's an electron, it's an antineutrino, or if it's a beta plus particle, it's just a neutrino. There's also gamma decay, which is basically the release of energy from an unstable nucleus to make the nucleus stable again. Photons were originally thought about by Albert Einstein in 1905, who came up with the idea of parcels of light, and the energy of these parcels was determined by the frequency of the particle. And he derived this formula called E equals hf. Energy equals frequency times Planck's constant. Now, Planck's constant is 6.63 times 10 to the minus 34 joule seconds, which is just a number you need to know. It's on your data sheet, so you don't really need to know it that well, but it's probably just worth knowing. You can also write this as E equals hc over lambda, because frequency is equivalent to speed of light over your wavelength, so you can learn either, they both suffice, and you'll probably need to use both anyway. Now, the other thing that they came up with was the idea of an electron-volt. Now, an electron-volt is the energy one electron acquires when it moves through a potential difference of 1 volt. Now, you know that voltage is work done over charge, and therefore, if you simplify this, it comes out as charge of 1 electron is 1.6 times 10 to the minus 19. And this is the definition of an electron-volt. So 1 electron-volt is 1.6 times 10 to the minus 19 joules. Now, if you have the energy, say, of a photon or of anything, you can convert it into electron volts by simply dividing it by 1.6 times 10 to the minus 19, which is obviously 1 electron volt, and that gives you an answer of how many electron volts a particle has. In the early 1900s, Albert Einstein, believes that energy is equal to mass, looking at rest energy and the rest mass of particles, in the famous formula E equals mc squared. And in 1928, a man called Dirac, who's also a physicist, uses antimatter to explain the theory that Einstein comes up with. So we'll move on to the topic of antimatter. Antimatter is basically, well, the antiparticles that have opposite charge, the same mass and the same rest energy, and he comes up with 2 ideas. The first is annihilation. Annihilation is when antimatter and matter join together, so an electron and a positron, or a proton and an antiproton. Their rest energy in the form of mass is converted into photon energy. So you have 2 particles coming together, and when they collide, 2 photons are given off, each with obviously the same mass, but also the same energy, because momentum needs to be conserved. So they must be going in opposite directions, having the same mass and the same energy. Now, he simplified this. The energy of the photons after the collision is 2 times your Planck's constant times frequency, because photons are effectively energy equals hf, as you recall. Now, the energy before is the energy after, because momentum is conserved, and the energy of the particles before is equivalent to the kinetic energy of the particles plus 2 lots of rest energy, because there's 2 particles, equals 2hf. Now, you can get rid of kinetic energy if you wanted the minimum energy, so this creates 2 rest energy equals 2hf, so 2 lots of energy. So therefore, the rest energy is equivalent to hf minimum, so that's like the minimum energy for the reaction to take place. Now, there was also pair production. Now, pair production is the exact opposite. Instead of a particle and antiparticle colliding to make 2 photons that go off in opposite directions, it's a photon that forms a particle and an antiparticle. Now, the same rules apply. There's the energy before must equal the energy after as momentum is conserved, The rest energy is calculated by E equals mc squared, which I don't think I've stated before. So find your mass of the particle times by the speed of light squared. The speed of light is 3 times 10 to the 8 meters per second. Well, this one's slightly different because you know, well, again, it's HF equals 2 lots of rest energy plus kinetic energy. Therefore, the minimum energy we can get with kinetic energy, assuming that the minimum energy is just the rest mass. So it's equivalent to HF, which is your energy of the photon, is equal to 2 lots of rest energies plus 1 for the particle and 1 for the antiparticle.
There are 4 fundamental forces in physics. These are the strong nuclear force, the weak nuclear force, the electromagnetic force, and gravity. The strong nuclear force only affects particles made up of quarks, so baryons and mesons. The strong nuclear force keeps the nucleus together, otherwise the protons in the nucleus would repel each other. Between 0 and 0.5 femtometers, the strong nuclear force repels protons away from each other. Between 0.5 and 4 femtometers, it acts as a force of attraction which holds the nucleus together. A distance greater than 4 femtometers means that the strong nuclear force becomes negligible. The exchange particles in the strong nuclear force are pions and gluons. Meanwhile, the weak nuclear force affects all particles. The exchange particles are either W+, W-, or Z bosons. Of course, this depends on the reaction, since charge must be conserved. The electromagnetic force only affects charged particles. The further the distance between nucleons, the weaker the repulsion of the electromagnetic force. The exchange particles are virtual photons.
The famous physicist Richard Feyman, who was famed for a number of lectures that have been turned into numerous books and that kind of thing, came up with a diagram that explains the really complicated kind of equations that are used to work out interactions between particles, hence named Feyman diagrams. Now, Feyman diagrams are made of a few things, or a few rules to remember when you're using Feyman diagrams. Straight lines are for particles, wiggly lines are for the exchange particles, everything must be connected together, and there should only ever be one exchange particle. Now, as was said previously, electromagnetic force, it's virtual photons, the weak nuclear force is W plus W minus Z bosons, strong nuclear force is pions and gluons. Now, electromagnetic force is for any particles charged, weak nuclear force is for anything, strong nuclear force is for hadrons, as has already been said. The strong nuclear force is a longer range because the pions are lighter than the bosons, and therefore they can travel at faster speed. There are 3 types of quark that you need to know for A-level physics. There is up, down, and strange. Up has a charge of 2/3, down and strange both have a charge of -1/3. There are also 2 types of leptons that you need to know, which are electrons and muons. There's also electron neutrinos and muon neutrinos, and the corresponding antiparticles of all of those. Now, all of matter is made of 2 types of two components, hadrons and leptons. Hadrons are made of quarks. They can interact via the strong nuclear force, electromagnetic charge decay via the weak interaction. There's also leptons, which aren't made up of quarks, and they can only interact via the weak electromagnetic force. Now, hadrons are made of baryons and mesons. Baryons are made of 3 quarks, or 3 antiquarks, or a mix of the 3, or a mix of the 2, should I say. Decay products include protons, and protons is the most stable particle, and there's also mesons, which are made of a quark and an antiquark. Particles, or some particles, can have strangeness. Strangeness is caused by the fact that they have a strange quark in them, or an anti-strange quark. Now, strangeness must be conserved in a reaction with the strong nuclear force. It doesn't have to be weak nuclear force. The other thing that you must be aware of is that charge, lepton number, and baryon number must be conserved in both reactions with the strong and the weak nuclear force, whereas strangeness, as I've said, is only the strong nuclear force, not necessarily for the weak nuclear force. Now, some particles have a strangeness of either -1 or +1. Now, if it's got a strangeness of +1, it must be an anti-strange particle. If it's got a strangeness of -1, it must have a strange quark in it. Now, we'll take the K-, for example. The K- has a charge of -1 and a strangeness of -1. Therefore, you know it must have a strange quark because the strangeness is -1. Now, a strange quark also has a charge of -1/3, but you need the charge to be -1. So we can use an anti-up, and as a K- particle is a meson, it must have a quark and an antiquark. So using simple deduction, you can conclude that the particle must be an anti-up. So hence the quark composition of a K- particle is an anti-up and a strange. Now, the K0 can actually be made of two different particles. K0 or K-, they're all kaons. Kaons can also decay into pions. And pions, as we know, are the exchange particle in the reaction with strong nuclear force. Now, kaons are made up of, again, they're mesons, so they're made of quark and antiquark. Now, a K0 particle can either be made of a strange and an anti-down, because that levels as a charge of 0 and has a strangeness of -1, or an anti-strange of a down, which again has a charge of 0 but a strangeness of +1. Now, there's also pions, as I've mentioned earlier. Now, a pi0 is a strange and an anti-strange, an up and an anti-up, or a down and an anti-down. A pi plus is an up and an anti-down, and a pi minus is an anti-up and a down. There's also the K plus, or a pion, which has got a charge of +1. This is made of an anti-strange, which means it's a strangeness of +1, and also an up. In the strong nuclear force, as I've said, baryon number, lepton number, charge, and strangeness all must be conserved.